Dear students, welcome back to Electromagnetic Waves and Transmission Lines course. Today we will discuss Module 5, Transmission Line 2. Here we will discuss input impedance relations, reflection coefficient, VSWR, average power, shorted lines, open circuited lines, and matched lines, low loss radio frequency and ultra high frequency transmission lines, ultra high frequency lines as circuit elements, and finally Smith chart, construction and its applications, quarter wave transformer, single stub matching, and illustrated problems. First, we will discuss about what is phase velocity and group velocity. Phase velocity and group velocity. Um, First, propagation constant gamma is equal to alpha plus j beta, where alpha is the attenuation constant, beta is the phase constant. Uh, for wave propagation, the voltage wave equation V of z comma t is proportional to e power j omega t minus beta z. The phase velocity is defined as the speed at which a constant phase point travels along the line is called phase velocity. For constant phase, omega t minus beta z is equal to constant. That is, by differentiating that equation, omega dt minus beta dz is equal to 0. That is, dz by dt is equal to omega by beta. Here dz by dt is called the phase velocity. Vp is equal to omega by beta. For lossless transmission line, the phase velocity Vp is equal to 1 by square root of Lc. Since beta is equal to the phase constant is equal to omega square root of Lc, omega by beta is equal to phase velocity. Therefore, omega by beta is equal to Vp is equal to 1 by square root of Lc. For distortion-less transmission line, also the phase constant beta is equal to omega square root of Lc. Here also the phase velocity is equal to 1 by square root of Lc. Now, group velocity is defined as it is the speed at which the envelope of a modulated wave travels. The group velocity Vg is equal to d omega by d beta. For lossless transmission line, since beta is equal to omega square root of Lc, dB by d omega is equal to square root of Lc. Vg also equal to 1 by square root of Lc. For lossless transmission line, Vg is equal to Vp. For dispersive transmission line or general lossy transmission line, the phase velocity varies with the frequency. If beta is not proportional to omega, then the phase velocity is not equal to the group velocity. Then Vg is equal to dB by d omega whole power minus 1. For important observations here, for lossless transmission line, the phase velocity and the group velocity is same. For lossless and distortion transmission line, the phase velocity and group velocity are same. For lossy transmission lines or dispersive transmission lines, the frequency is dependent on the phase velocity. So the phase velocity and group velocity are different. Now, the transmission lines input impedance. Here, will see the transmission line of length z is equal to 0 to z is equal to L. Here Vg is the transmission line connected to the generator and ZL is the load impedance. Here ZIN is the input impedance. ZIN is equal to VIN by IIN. From general voltage and current equations from transmission line theory, Vs of Z is equal to the forward wave and the reverse wave. Similarly, the current wave equation equal to forward current wave and reverse current wave, and the propagation constant gamma is equal to alpha plus j beta, and the characteristic impedance Z0 is equal to square root of R plus j omega L by G plus j omega C. Now applying the boundary conditions at the load Z is equal to L, the voltage Vs of L is equal to VL, Is of L is equal to IL. From equation 1 and equation 2, you can write VL is equal to V naught plus e power minus gamma L plus V naught minus e power gamma L. From equation 2, IL is equal to V naught plus divided by Z naught e power minus gamma L minus V naught minus divided by Z naught e power gamma L. Multiplying equation 4 with Z naught, you will get Z naught into IL is equal to V naught plus e power minus gamma L minus V naught minus e power gamma L. Now solving for V naught plus and V naught minus, by adding the equation 3 and equation 5, you will get V naught plus is equal to VL plus Z naught IL divided by 2 e power gamma L. Similarly, subtracting the equation 5 from equation 3, we will get V naught minus is equal to VL minus Z naught IL divided by 2 e power minus gamma L. Evaluating at the input Z is equal to 0, from equation 1, we will say that when Z is equal to 0, Vs of Z is equal to Vin, that is Vin is equal to V naught plus V power V naught minus, since Z is equal to 0. Similarly, the values of V naught plus and V naught minus will substitute here. By rearranging the terms, we will get Vin is equal to, this is the expression. Here, the hyperbolic function of cos hs is equal to, hx is equal to e power x plus e power minus x by 2. Similarly, sin hyperbolic x is equal to e power x minus e power minus x by 2. So by rearranging these terms, you can write Vn is equal to VL cos h gamma L plus Z naught IL sin h gamma L. From equation 2, also we'll get IIN is equal to, this is the equation. By substituting this V naught plus and V naught minus in this equation and simplifying that, we'll get IIN is equal to VIL divided by Z naught into sin hyperbolic gamma L plus IL cos hyperbolic gamma L. From input impedance, ZIN is equal to VIN divided by IIN. By substituting equation 8 and equation 9 in the above equation, we will get this expression, and factor IL using ZL is equal to VL by IL, ZIN is equal to ZL cos hyperbolic omega L plus Z naught sin hyperbolic gamma L. Similarly, here ZL by Z naught sin hyperbolic gamma L plus cos hyperbolic gamma L. Now, by multiplying the numerator and denominator by Z naught, we will get ZIN is equal to Z naught. ZL cos hyperbolic gamma L plus Z naught sin hyperbolic gamma L divided by Z naught cos hyperbolic gamma L plus ZL sin hyperbolic gamma L. The alternative compact form for the input impedance of the transmission line. Now, dividing the numerator and the denominator by cos hyperbolic gamma L, we will get the expression in terms of tan hyperbolic gamma L. That is ZIN is equal to Z naught, ZL plus Z naught tan hyperbolic gamma L divided by Z naught plus ZL tan hyperbolic gamma L. For lossless transmission line case, the attenuation constant alpha is equal to 0. The propagation constant gamma is equal to alpha plus j beta. Alpha is equal to 0. Therefore, gamma is equal to j beta. We can write the input impedance for lossless transmission line ZIN is equal to Z naught, ZL plus Z naught tan hyperbolic gamma L. Gamma is equal to j beta L. Then we can write this is equal to j tan beta L. Okay, this is a very simple expression. Similarly, for the denominator also Z0 plus JZL tan beta L. Okay, here we can see the hyperbolic and trigonometric identity tan H Jx is equal to J tan X. Okay, for the property of lossless transmission line, R is equal to 0, G is equal to 0, the propagation constant gamma is equal to J beta. Now the final result for the input impedance of transmission line Zin is equal to Z0 into ZL plus JZ0 tan beta L divided by Z0 plus JZL tan beta L. Now the transmission line equivalent diagram for input impedance you can write here. This is a generator side, this is a load side, this is Zin. Here this is a VIN. VIN is equal to VG into ZIN divided by ZIN plus ZG. Similarly, IIN is equal to VG divided by ZIN plus ZG. This is a generator impedance. The input impedance for different lengths of transmission lines, we'll see the transmission line length L is equal to lambda by 8 and transmission line length L is equal to 2n plus 1 to lambda by 4, and case 3 the transmission line length L is equal to n into lambda by 2 where n is equal to 1 to 3 and so on. For case 1 the transmission line length L is equal to lambda by 8, the general input impedance Zin is equal to by substituting L is equal to lambda by 8 in the input impedance equation, beta is equal to phase constant, beta is equal to 2 pi by lambda, where L is equal to lambda by 8. Therefore, beta into L is equal to pi by 4. By evaluating this tangent tan beta L, that is equal to tan of pi by 4, that is tan 45 degrees is equal to 1. Substituting it into this value in the input impedance formula, Zin is equal to Z0 into ZL plus JZ0 divided by Z0 plus JZL. Therefore, the magnitude of Zin, this is equal to Z0. Now, we have the case 2 where the length L is equal to 2n plus 1 to lambda by 4 for lossless transmission line. The general input impedance formula here is given here. Now, substitute beta into L. L is equal to, suppose when n is equal to 0, L is equal to lambda by 4. When n is equal to 1, L is equal to 3 lambda by 4. Now, substitute n is equal to 0 here. Beta into L is equal to 2n plus 1 to pi by 2, and tan of 2n plus 1 into pi by 2, tan pi by 2, that is equal to infinity. By substituting this value in the impedance equation, Zin is equal to Z0 JZ0 by JZL. Now Zin is equal to Z0 square divided by ZL. Okay, when length L is equal to lambda by 4, then the transmission line is called quarter wave transmission line. L is equal to lambda by 4, therefore beta into L is equal to 2 pi by lambda into lambda by 4. This is equal to pi by 2. Since tan pi by 2 is equal to tan 90, that is equal to infinity, the input impedance Zin is equal to Z0 square divided by ZL. Now coming to the case 3, the length L is equal to n into lambda by 2. When n is equal to 0, when n is equal to 1, this is lambda by 2. Now the beta into L is equal to 2 pi by lambda into lambda by 2. Therefore, beta into L is equal to n into pi. By evaluating this tangent tan n into pi for different values of n, this is equal to 0. By substituting this into the input impedance formula, Zin is equal to, this value is 0, therefore Z0 into ZL by Z0. Therefore, For length L is equal to n into lambda by 2, the input impedance is equal to the load impedance. For the transmission line length L is equal to n into lambda by 2, the input impedance is nothing but the load impedance. Similarly, the input impedance for different load conditions, we'll consider first one is Z is equal to 0 is called short circuited, and ZL is equal to infinity is called open circuited transmission line. First case, the short circuited transmission line ZL is equal to 0. The input impedance of a short circuited transmission line, short circuited means ZL is equal to 0. Therefore, ZIN is equal to, by substituting ZL is equal to 0 in the input impedance equation, ZIN is equal to Z0, J Z0 tan beta L divided by Z0. Input impedance when load is short circuited is denoted by ZIN is equal to ZZC. This is the short circuited transmission line input impedance. That is equal to JZ0 tan beta L. Similarly, the open circuited transmission line input impedance, that is denoted by ZOC, open circuited transmission line input impedance. This is equal to ZL is equal to infinity. By substituting this ZL is equal to infinity in the input impedance equation, ZIN is equal to Z0 1 by J tan beta L. Since 1 by tan x is equal to cot x, you can write the input impedance when the load is open circuited is denoted by ZIN is equal to ZOC. Therefore, ZOC is equal to minus J Z0 cot beta L. Now, the relationship between the open circuited and the short circuited input impedance is given by ZSC into ZOC is equal to Z0 square. Or you can write the Z0 is equal to square root of ZSC into ZOC. Z0 is the characteristic impedance. Dear students, in our next class we'll discuss about the reflection coefficient. Thank you.